And a premium account.
We are live.
Okay, we are live right now. All right, so I would like to welcome everybody. This is Dr. Pete, and today is a live show, and it's a special show. I have two other guests with me, and we're going to be talking about fructose, glucose, the polyol, fructose uric acid pathway. And we are also going to talk about how this important pathway, which I believe it directs chronic metabolic diseases when it's chronically activated. We're also going to hear from one of the guests, Neil Gyte, who brings a practicality to this. And as the host, will be asking us questions. Now, I don't want to go on too long, so I'll just give my brief biography. My name is Dr. Pete Delanoy. I've been doing this now, or in this space, for almost 7 years. And I got into this because 7 years ago, I was diagnosed as being pre-diabetic and a gout sufferer, and was trying to understand how that could have happened to me because I was still relatively active. And I believed at the time I was eating a healthy diet, and these things were not the case. And when I went to the medical establishment to try and find a solution to this issue, what I heard was to get more exercise. I was a third-year CrossFit athlete at the time, and to eat a Mediterranean diet, which also at the time I was doing that, although I was still eating a significant amount of sugar and drinking alcohol chronically, and didn't understand at the time that you couldn't just work that stuff off. So for me, this started a journey as a biochemist to go deep into the literature to try and understand the biochemistry that I think ultimately drives these metabolic diseases, in order to understand what causes them, so that we can make better decisions about our lifestyle so we don't get sick in the first place. And with that, I'll turn over the talk now to Dr. Richard Johnson.
Thank you, Dr. Pete. I'm Rick Johnson, Dr. Rick Johnson. I'm a professor of medicine, now emeritus at the University of Colorado. I've been doing research since I started medical school. And so over the last decades, I'm both a clinician who takes care of patients, but I spend a lot of time trying to figure out the causes of disease. And even though I'm a kidney specialist by trade, I found my research migrating from the world of the kidney to what drives obesity and diabetes. And proudly, for the last 25 years, I really have focused on trying to understand what causes these diseases, why people are prone to getting fat, what we can do about it, why are all these metabolic diseases related. And that took me to the discovery that there was a specific type of sugar, fructose, that seems to be, or fructose, you can say it either way, that seems to be really important in this biologic pathway that leads to obesity and diabetes. And I have studied it quite a long time, and I've written several books on it. Most recently, Nature Wants Us to Be Fat. And I'm happy to be on the show. And Pete, it's great to see you again. We've been collaborators over the years too. Okay, Neil.
Thank you very much. So I have a very different background to Pete and Rick, and relatively new to the metabolic health game, but for very good reasons. So I spent 20 years largely in the tech world, 12 at Google, helping to build Google Maps, Google Earth, and the business around that. I'm now on a new mission as of January this year to try and help 1 billion plus people become metabolically healthy. And that switch was driven actually largely, hugely influential by Rick, by your book, Nature Wants Us to Be Fat, which is just over my shoulder here. Because reading that, and we'll get into this a little bit, literally, honestly, blew my mind with what I read in there, and it helped piece together a number of things that I had experienced on my own personal health journey, from being 260 pounds, 18 stone back 10 years ago, to doing ultra endurance things. But it was really the impact of chronic disease on close family and loved ones through a range of different diseases, from cancer to bipolar to depression, and these diseases, I started seeking the root cause, how you could prevent and reverse them. And that took me through the work of Dr. Thomas Seyfried and ultimately your work, Rick, to kind of understand that our mitochondria and metabolic health is the root cause of all of these chronic diseases, and the majority of them are preventable and reversible. So when I realized that, I decided to leave the world of tech and embark on this new mission, which is comprised of two parts, really. One part is really awareness and education, because I thought I was relatively clued up on, food and nutrition and health. And I realized how little I actually knew. And therefore, there's so many people in the world who don't understand our evolutionary biology that really need to. And so as part of that, I have a website, 1bmh.org, we can link in the show notes. And I'm doing challenges to raise awareness for this, which we'll maybe talk about my upcoming swim challenge a little bit towards the end of the podcast today. And then the other part of my kind of path right now is really trying to support products that can impact billions, practical, useful products that can help people get back in more in tune with their biology. And so as a result of that, I joined RX Sugar as Chief Business Officer. And RX Sugar is a health and wellness company disguised as a food company, really laser focused on minimal natural products designed for blood sugar control and satiety. And we'll obviously talk about allulose a little bit today, which is one of the main ingredients we formulate with. So yeah, that's a little bit of intro about me. In that case, I would say I'll take it away and start at least the first half of this as we dig into what is the polyol pathway and how it impacts metabolic health. And so, Rick, I'd love to start with you, because reading your book, Nature Wants Us to Be Fat, you absolutely blew my mind. And the only way I can relate this to when people watch Star Wars. So I watched Star Wars with my daughter, and when Darth Vader utters those famous words of Luke, I am your father, just seeing the mind kind of just turn at that point. I remember first time I watched it, but reading your book, Nature Wants Us to Be Fat, I knew at the time how metabolically damaging fructose was, but I had no idea that our bodies can create fructose internally, even when you don't consume any fructose. So could you maybe talk us through a little bit what this pathway is, how you discovered it, and its impact on metabolic health?
Yes. Well, thank you for the kind words. Actually, it's really quite nice that you relate me to Darth Vader. Anyway,
you're more Luke Skywalker than Darth Vader, but it's more.
Nature wants us to.
Or maybe Obi-Wan Kenobi.
Well, but let me just tell you, it was a circuitous, very long route of discovery. There were a lot of surprises on the way. Many things that happened that kind of shook the science as we've been describing it, and as we've been thinking it. As you know, for decades, people have thought that the way you get fat is you eat too much and you exercise too little. It's supposed to be that simple, but we know it really isn't that simple. And there is this magic with going on a low carb diet that was discovered some years ago by Atkins and others, and this wasn't totally compatible with a calorie based system. And so there's been this issue going on where people say, hey, you should cut back on fats because they contain all the calories. But what people find is that when they reduce carbs, that really seems to be a more powerful way, not just to lose weight, but also to become metabolically healthy. So I kind of traveled through this thing where I was a kidney doc trying to understand high blood pressure. High blood pressure is known. The kidneys are known to have a problem with excreting salt and high blood pressure. And it took me on a long route, and I won't bore you with all the things, but basically what we discovered was that subtle damage, very, very subtle damage to the kidneys makes the kidneys start to hold on to salt. And people who develop hypertension have this subtle injury in their kidneys. And we ended up writing a New England Journal thing on this. And And I think it's true that although genetics plays a role, the subtle damage to the kidneys is actually the mechanism driving most high blood pressure. And when we were trying to understand what caused the subtle kidney damage, we found that we could do it 20 different ways. But there was one way that was particularly exciting, and that was just by raising uric acid in an animal. Over time, they would get subtle damage to their kidneys. And interestingly, the uric acid itself, when we raised it, blood pressure went up, and in these laboratory animals. And it caused kidney damage. And what we found is once the kidney damage was there, you could correct the uric acid, but the high blood pressure persisted. So then at that point, I met up with a young doctor who was running a big hypertension clinic in Houston, where there was a lot of obesity, and he had a lot of these kind of obese adolescents, 14, 15-year-olds with, who were developing obesity and diabetes and high blood pressure. And we found that they had a high uric acid, and we did a controlled clinical trial, placebo, blinded. And when we lowered the uric acid in these kids, we corrected blood pressure in 90% of them. We published it in the JAMA. It was a big deal. It was one of the bigger papers that year in the world of hypertension. And it sort of told us that uric acid seemed to be important in the initiation of high blood pressure. Because when we lowered uric acid in older people who already had some kidney damage, it wasn't as impressive as it was in the adolescents. So it was kind of an initiation, but not persistence. And then we said, okay, what's driving the uric acid? And actually, you probably know Gary Taubes. Gary actually was a reporter back then, and he called me. This was around 2004. And he hadn't written about sugar at that point or about carbs. He was still thinking about other things. But when he called me, he asked me, what, because I had written a little editorial with the New England on this pathway, on uric acid being important in more than just gout. And, he said, well, what do you think's driving the uric acid up? And I said, well, it can't really be purines and red meats because they're not really going up dramatically like this rise in blood pressure and obesity that we're seeing. But sugar can do it. And he said, yes, sugar, yeah. And we started talking about sugar, and I realized that I needed to do some studies with sugar, because sugar contains this sugar called fructose, and fructose actually, when it's metabolized, it generates uric acid. And so when we gave the fructose to these animals, laboratory animals, they developed high blood pressure, the uric acid went up, and we lowered the uric acid and we lowered their blood pressure. And suddenly we had a mechanism for what was driving the uric acid up in our adolescents. And fructose is in high fructose corn syrup, and it's in table sugar. And it turned out that these kids were eating huge amounts of sugar. And the most exciting thing was that when we lowered the uric acid, we improved all that. The rats didn't gain weight as much. They didn't develop fatty liver as much. We had benefits on insulin resistance. And then when we went back and looked at our JAMA paper, we actually blocked weight gain and improved other parameters in those kids too, in the people, in the humans. And so then we go, oh my gosh, fructose is really important in driving obesity. And maybe that's why the low carb diets are working. And then because carbs include sugar. And then what we did is we started studying the fructose, and we realized it was driving more than just obesity and fatty liver and diabetes, but it was actually causing brain effects. It was making animals hungry. It made them forage. We got all these different things going on. And then we realized that this was all driven by fructose. And then we found out that the way it was working was that there was this paralysis of the mitochondria. I'm sorry, I'm speaking so long.
No, you're fine.
Anyway, real quick, I'm going to get up there so we found that these mitochondria, which are these little things in our cells that make energy, were being suppressed by the fructose. And that was the big real break when we figured out that fructose was blocking the production of energy, blocking the production of ATP. And the reason we get hungry is because our ATP levels are dropped, and that triggers hunger and all those things. And, it used to be thought the way people get obese is you just eat too much and you kind of fill the tank up with ATP, and then the excess energy goes to fat. But what actually happens to gain weight, you have to drop the energy in the cell, the ATP, that triggers you to gain weight. Anyway, so that was kind of the big discovery, that fructose was the only nutrient that lowered ATP to any extent. Alcohol did it too a little bit, but fructose was the big player. So that kind of took me into, why would that nutrient do it? And then we realized that it was used in nature by animals in the wild to help them gain fat. And then we realized there was an evolutionary basis. I mean, it kept getting bigger and bigger. And then we had this incredible thing, because I knew that French fries was bad, right? We all know French fries are bad. And French fries are salt, and they've got oil, and they've got potatoes, and potatoes are starch. There's no fructose in potatoes. And then came the discovery that from our group that the starch was being converted to glucose, and the glucose was being converted to fructose in the body. And we call that, it goes through a special pathway called the polyol pathway. And then we started studying, we realized that this was actually a major pathway for making fruit, for the way animals can make fructose. Not a whale can't find, honey and fruit. It's eating, fish and so forth. So how does it trigger fructose? It does it through endogenous production of fructose. And so it turns out that endogenous, meaning that it's made within our body. And so, but it comes from carbs. All fructose comes from carbs. It comes from glucose. So the low carb diet still works, because not only is it blocking sugar intake, it's blocking foods that raise our glucose that then get converted to fructose. So I'll stop there.
So thanks, Rick. Maybe just to tie a couple of things together from that. So for me, when I read all of this, I think the critical thing is, mitochondria are the powerhouse of our cells. They create energy in every single cell within our body. They actually make up 10% of our body's body weight. And without the energy sources, none of our cells and none of our organs can function correctly. So what blew my mind was fructose damages the mitochondria, so they can't produce energy. Therefore, any cell or organ is not producing energy correctly. And I think largely people realize that, sugar and fructose, if you consume that, then that is not good for you. But what blew my mind is, even with no exogenous fructose, too much carbohydrates is one of the things that can trigger the body to create that internally. So then you're damaging mitochondria. So all of these different chronic diseases that happen in different organs can be triggered, through this pathway. So I think that's a really great summary. Pete, I'd love to bring you in now and kind of just get your perspective on when you understood kind of this pathway and the carbohydrate link, and what your
Pete has
become
Pete has become a world expert on the polyol pathway. He really has. So
my it's what I want to say to start is that when I originally went to a ketogenic diet to reverse my prediabetes, I knew I was a gout sufferer, and I'm like, what's going to happen to my gout, right? And in our low carb space, we hear about that. People are like, well, is keto safe if you're a gout sufferer? So I went to the literature, and I'd already been in there trying to understand whatever I could about the ketogenic diet historically, going back a couple hundred years. And so I started asking questions about the gout, the story of gout, and jumping to the end conclusion of this, I realized when I got to Richard Johnson's work, as soon as I started reading the fructose uric acid papers, it was like I had the same epiphany that you did, Neil, about this. I was like, this guy has the pathway. This is the pathway, right? What I need to do is find out if this pathway is operational in the biologically important cell in the joint, the chondrocyte. And when I went there, I found a ton of circumstantial evidence was there. And I'm like, okay, well, what about the fructose? But when you look at the fructose, you find out that after the fructose is basically come past the intestinal, I don't want to get too off track here, but once it comes through the intestinal tract and reaches the liver and yada, yada, then once it's into the peripheral circulation system, it's relatively low concentration. And so I'm like, okay, so then what's going on with the chondrocyte? And I came upon this paper that was published in 2015 by some French guys. Lead author was Laiguian, and they identified that the polyol pathway was functional in the chondrocyte. And I was like, boom. And then when you looked at the glucose situation with it, it was operating like most of the other cellular systems in a human. You know, when hyperglycemia showed up, there it upregulated the GLUT1 transporter and flooded glucose into the cell and activated polyol. And when you put it in that context, and in other contexts too, the lactate effect, the elevated lactate, which gets pushed into the extracellular matrix, along with, and this is the thing, if you read the really early literature, Krebs and Veitch, and even before that, Warburg, we know that when lactate gets pushed out, like any other negatively charged molecule into the extracellular matrix, it takes a proton with it. And we know that when you acidify the extracellular matrix, that you dump calcium out of the extracellular structure that's there. And you need calcium ion to initiate the crystallization of uric acid. So if I could demonstrate how I felt when I read that, I would have fallen out of my seat, because I'm like, okay, this guy has this. Now, when I got into this, I also realized when I read most of these papers, which is a lot of them, that I agreed with Dr. Johnson about the evolutionary component to this. And I realized, because from my point of view, I was searching at this point for a biochemical argument for a central mechanism that is natural to all of us.
Yeah.
That is being hyperactivated or chronically activated and being held in this state day in and day out and so forth, down, year in and year out, that eventually would drive chronic metabolic diseases. Because I think there's one central pathway. There's not, when you make a list of all these chronic metabolic diseases, I think if you believe in, if you're a good scientist, you can't look at that and go, okay, well, there's going to be 15 or 20 different mechanisms for each one of these things. We should be able to come all the way back into a central mechanism, and then we explain the diseases based on our differential genetics. We all have the same genetics, but we all have nuances with this, how we respond to this environment. And I've been now health coaching for 6 years, and I've seen you can break people out into these really simple categories. I think it's more complicated than that, but it's pretty obvious after doing this for a little while that you've got these thin people that are super metabolically sick, and you have the obese, and all of us have these overlapping diseases. So when I saw the result with the polyol in the chondrocyte, then I started looking harder for polyol in all of our different tissues and all of the different organs. And truth is, you can find it. It's ubiquitous, and in a tissue where some might argue, well, it's not there, but they haven't looked yet, is what it boils down to. And when you look carefully, you find it. The other thing is aldose reductase is and its family of enzymes, right? It's not, there are different isoenzymes, but when you look at this, they all have different functionalities. And there's a lot of investigators that have looked at aldose reductase and think it's important, but argue, well, you need really high levels of glucose to activate it. And this isn't true. When you look at the early literature in regard to aldose reductase, you find out that it has an unactivated and an activated form. It's a very interesting enzyme because it's monomeric. And I know I have the risk of getting really technical here and want to try to avoid doing that, but it's unusual because most enzymes that are involved, many of them that are involved in our metabolism are really complex. Like everyone seems to know about hemoglobin and carrying oxygen and how there's all these different subunits, or some of the subunits are the same, but that it's this complex thing. And aldose reductase is a single protein, single polypeptide. And the interesting thing is, so is glucokinase. These guys are ancient, right? And they are very complex when it comes to their regulation. And it was shocking when I learned, okay, aldose reductase can be activated. Now we're in a different zone. And the activators are more than one thing, right? It's activated not only by elevated glucose, but I believe in the same range as glucokinase, but also by NADPH and also glucose 6-phosphate, which is the primary product of glucokinase. And so when you start to think about this way, and then you systematically go back and take one step at a time and look at the biochemical and the molecular evidence, the tissue culture evidence, much of this coming from Dr. Richard Johnson and his collaborators, you don't find any contradictions. It's basically, once polyol gets activated, fructose uric acid is wide open. We get accelerated glucose. We get the downregulation of, we get elevated lactate. We see the inhibition of the TCA cycle by in a uric acid dependent process with NADPH oxidase. Citrate comes out into the cytoplasm, and we get de novo lipogenesis rocking right along. And in a paper that I just finished writing with Rick Johnson and my collaborators, and his all of our collaborators, it was a number of different authors. I think we've made a really good argument for this. It's not clean cut. It's not black and white. There's a lot more work that needs to be done in different parts of this. But basically, I think it's clear cut that once you open polyol, that the whole system is running essentially wide open. Yeah. And something that I haven't talked about yet, I have forewarned Rick that I'm going to be sending him another manuscript. But when you go into Krebs and Richard Veitch's work, I think, Richard, I might have misspoken that. It's R.L. Veitch. When you look at his work, and those guys came, I'll shut up in a minute, but those guys came to the conclusion that the classic central biochemical pathways, which everyone thinks are said and done, was only the tip of the iceberg. How these pathways are communicating between them, how we get the unidirectional flow from one pathway into another, and then how we modify what's going on with the mitochondria and then come back into the cytoplasm is really where the game is. Yeah. And they identified the fact that the coenzyme couples and the phosphorylation potential of the cell is what's driving this. And this goes back to the argument Rick was making about evolution. When we start to walk backwards in evolution, you come into simpler and simpler systems. And these small molecules, some of which you guys already mentioned the uric acid is one of these molecules. I'm convinced of it. And then you've got NAD and NADP plus, beta hydroxybutyrate, the ATP, the phosphorylation potential, which is a series of 3 molecules that are in a ratio, and so on. These at the core of it are driving the extent and the directionality of the choices between glycolysis, the production of fat, or the oxidation, and so on. And this is really at the core of this. So I'm going to be really bold and just step out, and then I'll shut up. I think when we talk about polyol fructose uric acid through de novo lipogenesis, that you're looking at the central mechanism in humans for the synthesis of fat. It's as important as looking at glycolysis individually or looking at the TCA cycle individually, and so on.
So thanks, Pete. So I agree with that. Let's put a pin. I'd love to, we'll pick up on this when we really look into, how do people generally know if this pathway is turned on and what turns on the pathway. Before we go there, I'd love to dig a little bit just into the evolutionary perspective, because I think this is something that fascinated me, which is, and Rick, this is covered by a lot of your research and your books, which is this fructose pathway, this polyol pathway. Actually, we have evolved over time to become more sensitive to it, because in times of food scarcity, it's actually saved us as a species. And it's maybe somewhat ironic that in the current modern environment, because we don't have food scarcity anymore, but our biology hasn't caught up, what was a survival switch that saved us, I believe, to tie into to Pete's kind of words, which is slowly killing, I would say, people, or creating these chronic diseases because of the overconsumption of foods and the lack of nutrients in food. So maybe could you touch a little bit on the survival pathway and how that is manifesting itself in the modern day world?
Yes. So we all know that the animals will respond under various conditions in different ways. So, but that there's some specific pathways. Like, for example, if you activate, if you put an animal in a dangerous situation where there's a predator, they're going to either run or they're going to fight, and their sympathetic nervous system gets turned on. And we've studied, the reactions under crisis, right? If you dehydrate an animal, it was well known that, that they go through some very specific responses. Or if they're starving, these are all critical crises. And so animals, they go into these kind of mechanisms to help them when they're in a critical situation, like with a predator or starvation. But often the response isn't good enough and the animal will die. So in nature, there was this big, it's always about, how can we help us survive a crisis. And the situation is that if you're in the crisis, it's too late in some respects, often. So if you could actually prepare for a crisis, that would be an incredible survival advantage. And we know that animals, in diverse environments, there can come winter where there's no food. And so animals have to prepare before there's no food. They have to find a way to either store it, and some animals will store little caches of food in their nest and so forth, so that when there's no food around, they can eat it. But then a predator can come in and they may have to move, and then their food's there and they're lost. So it'd be better if you could carry the fuel on you. And so, but you don't want to carry it year round, because then if you're fat and you've got your energy stores that you can use to help you survive when there's no one around or no food around, that's good. But you don't want to be like that year round, because a predator might find you quite easy to catch if you're too fat. So we realize that nature actually what is smart and knows that a lot of these animals somehow know that winter is coming, And like in the fall, suddenly they will start eating a huge amount of food and activate this biologic pathway so that they forage, they eat more, they drop their metabolism, they gain the fat, they gain the liver fat, they become insulin resistant. So it's like a normal response to help survival. It's meant to be it's meant to be a good, safe survival response. And it is, because they eat the food and they get fat, but then winter comes and then they hibernate, they don't eat, and they burn the fat. But in our situation, as you say, we seem to have activated this switch, but we aren't hibernating. We just keep eating. And so what becomes a little bit of fat that can help you survive the winter, and then you're back to normal. In this case, you keep eating and then you develop bad obesity and you get diabetic and you get all these conditions that we weren't meant to have. So what we learned is that this survival mechanism was meant to really help animals under stress. And we found that it not only does it help you to survive winter, but animals will use it in any kind of crisis. And in fact, when you have a heart attack, if you are so unfortunate as to have a heart attack, when there's reduced blood flow to the heart, that activates this survival pathway there. The trouble is that we have found ways to amplify it. And what was meant to be a survival response tends to be a bad outcome. And so we now know that when this process is activated with a heart attack, it actually causes more damage than good. And this is the problem when you've kind of hyperactivated this system. So most animals have very low uric acid levels, and they aren't eating very much sugar. They're eating maybe fruit, and then if they want to get obese, they'll eat a lot of fruit, or they'll make a lot of endogenous fructose. But we are just amplifying that dramatically. We had a mutation that makes us sensitive to sugar way back when, and and so we are more sensitive to sugar. We're more sensitive to fructose. We have higher uric acid than other animals. That's why we are more prone to gout, and that's coupled with the Western diet. It's a very bad combination. So what was meant to be a survival factor for animals in the wild and even for our species, in the Western world, with all the diets, high glycemic foods, ultra processed foods, salt, and all these things, and salt can activate this pathway too. So that's the problem. And so it's exactly what you said. It's an evolutionary pathway that was meant to provide survival. It did provide survival for many animals, even for us. But in today's society, we're kind of overdoing it.
Yeah, thanks, Rick. That was a great summary. I think from my perspective, one of the amazing things that I learned through all of this is that this is a very strong and powerful biological process, and that has evolved over millions of years, that if you're not living, I would say, in tune with your evolutionary biology, you're then fighting your evolutionary biology. And the current food environment, with the lack of nutrients, the added sugar, and generally I would say the high carbohydrates in many foods, actually creates a vicious circle, because then this pathway is activated, it damages the mitochondria, and when the mitochondria don't feel they're getting enough energy, they actually release ATP as a signal to say, as you mentioned, there's low energy, which forces us to be more hungry. But then if you're putting more of that, not very nutritious food, ultra processed food, high sugar in your body, you then create this vicious circle where the body's trying to save itself. So I think that was something that I understood. So I then looked at it, how can we live more in tune with our evolutionary biology? So maybe let's move on a little bit to, we've established this, we believe this is a central pathway, largely controlling mitochondrial health and metabolic health. So how can people know if this pathway is turned on? What are some of the ways, maybe Pete, that we can understand this? I know obviously kind of glucose levels is one thing. How can people know?
So before I try to answer that question, I want to come back to something that Rick and his collaborators published a long time ago. And then when he wrote Nature Wants to Be Fat, he talks about this switch. And I had mentioned just a little bit earlier that when I started looking at the evidence throughout this whole pathway, that you don't find contradictions. And in fact, let me just recount it. 1, 2, 3, 4, 5. There's at least 6 different molecular mechanisms involved in once you open the polyol pathway, starting with aldose reductase to the point where you're making the fat, that are operating as molecular switches or trapdoors. Like in the case of, if you imagine a trapdoor, you're standing on top of this thing and then it suddenly opens, boom, you go through it. That's fructokinase. Or it's phosphofructokinase, depending on how those 2 enzymes are being regulated at that moment. But and I call AR, aldose reductase, the gateway. Once it swings open, it's rock and roll time. And there's 5 or 6 other mechanisms in there. I'm not going to go there right now that are operating like switches. That's the thing that, Rick, what you got onto and intuited a long time ago is held up when you go step by step through this stuff. You just find it all the way through this process, that when substrate shows up, blam, you just are onto there's another gate or a really high capacity enzyme that just pushes everything right away to the next step of this. So that's a really interesting thing. And I think that's holding up super well with this. I think it was really smart to call it a switch, because I think ultimately that's what it is. Now, the polyol pathway, aldose reductase is a gateway, and it is being activated. And I know that in the paper we wrote, I argued for 90 mg per deciliter. Whether that withstands the review process, I don't know. But the way I made that decision on the glucose level was based on the KMs for those 2 enzymes, aldose reductase and glucokinase, and the way that they're being activated. Now, you and I, Neil, had a discussion about this already. Does that mean that the threshold is actually 90 mg per deciliter? No, it doesn't. What it does mean, though, is our threshold for how we think about hyperglycemia, I believe, is a lot lower than what you see in the literature and how doctors and how people think about this.
Yeah.
I have some data that would support that, Pete, that I don't think we've discussed. And there is this really interesting thing. So we have a mouse that cannot make fructose, and we have a mouse that cannot metabolize fructose. And in both situations, the mouse that can't metabolize fructose, he is protected even if he makes fructose. And what we found is that, if we give them sugar, they're protected from sugar, right? Because sugar has diet, it's filled with fructose. So if you give sugar to a normal mouse, they get fat, they get diabetic. But if you give it to this mouse that cannot metabolize fructose, it's protected. So that's all good, fine and good, right? That says fructose is bad. But here's what's really interesting. We decided to see how long these mice would live, because they're sort of living on a keto diet, sort of. And I mean, the sense that they cannot metabolize any fructose at all for their whole life. So we had mice that were on just a standard diet. Now, the standard diet for a mouse is, about 50%, 60% carbs. So it's kind of like our diets are like 50 to 60% carbs too, the average diet, but we have a lot of sugar in it, and we have a lot of fructose. But the diet the mouse eats has very little fructose in it, less than 1%. So they're not really getting dietary fructose, but they are getting a carb diet. And what we found and published was that these mice that could not metabolize fructose, and the blood glucose levels don't really, they're a little high in these animals, but It's not like putting them on a diabetic, diet to induce diabetes. But these mice were protected from aging, and they did
Mm.
not get aging changes in they maintained their blood pressure stayed normal with age. Their blood vessels were better with age. Their kidneys, with aging, you start getting disease in the kidneys. They were completely normal. And there is some evidence that centenarians have a low uric acid level, suggesting that they're not making much fructose or metabolizing fructose. And
Yeah.
so I think that these animals, that we're all making fructose, even when your blood glucose is not so high. Even when you think you're normal, you still are probably producing some fructose that over time can cause some aging effects. And
Yeah.
so my belief is that low carb diets may actually be good for aging, to help prevent aging. That low intermittent fasting, where you kind of reduce your exposure to sugars and carbs, at least intermittently, that the benefits there are also related to reduced carb load, reduced and a low uric acid might be a biomarker that would suggest that you're less likely to get metabolic disease. In fact, if you look in clinical trials, I show a slide. If you look at the general population and you measure serum uric acid, if your uric acid is like under 5, your chances of having high blood pressure, diabetes, kidney disease, hypertension goes way down. So, I mean, we consider normal as less than 6 or less than 7, right? But actually, if you have a uric acid of 4 or 5, you are at a much better chance of not developing high blood pressure and obesity than another person. And in fact, they did a study with 65-year-olds, and they measured the uric acid, and then this was done retrospectively because they looked at how long they lived, and so they had the ones that made it to 100 and the ones that didn't. And the ones that didn't make it to 100 had a higher uric acid level at age 65 than the centenarians to be. So if you have a low uric acid, it protects you from dementia, protects you from obesity, and so forth. It really does. Now, there are exceptions, right? There's going to be someone with a uric acid of 4 who's overweight, and there are other mechanisms for obesity. This is just what we think is a main one. But I think serum uric acid is a really good biomarker, and I think it really is a great predictor. And fasting blood sugar and fasting insulin probably are good predictors. Hemoglobin A1C is probably a good predictor. What you eat is a good predictor.
So I agree. So I'd love to actually just to tie this together, because even learning this was kind of interesting for me. So to maybe summarize and help how I think rationalize this from an evolutionary perspective. So generally around a glucose reading of around 90 milligrams per deciliter can potentially be around the threshold that the switch activates. Now, just to put that in context, generally when people go to the doctors for their checkups and they get a fasting glucose test first thing in the morning, having not eaten, I think generally between 60 and 85 is deemed to be a healthy fasting glucose score. And so what amazes me is then if you look at 90 or even 100 as a threshold, then pretty much every meal that people consume, if it's high in carbohydrates, is going to spike you way over that. Generally, even if you are sensitive, your glucose will spike up to 120, 130, and other people it can be in the 200s and above. And so every time you're eating, you're actually flicking and activating the switch. And the way I think about this from an evolutionary perspective is our biology can only tolerate 1 teaspoon of blood glucose in our 6 liters of blood. So if you think about that from an evolutionary perspective, just because of the way we've evolved prior to the agricultural revolution and the introduction of grains into our environment, that actually, our bodies aren't designed to tolerate huge amounts of carbohydrates and sugar. But when they do, they then promote fat storage because it's back to this survival mechanism. So tying all of this together, I think it's really important that people understand that every time you have these elevated glucose levels, you can be triggering this switch. And so I think you've touched on some of these, Rick. If people want to understand, how can I effectively understand where I'm sitting with this? It sounds like blood glucose monitoring, fasting, as well as after meals with something like a Keto Mojo is really important, as well as A1C, uric acid, are kind of, I would say, the main ways that people can test.
I do want to make one comment that it's extremely difficult to keep your blood sugar under 100 after most meals. And there are, so I would, even though 90 may be where it starts to be made, it is incremental. It isn't like you turn the switch on at 90. It's just, it activates. It's like a dimmer switch, right?
Yeah.
So, and there is one study that was done with children, looking at, how important it is for a breakfast for children to do well in school. And it's been actually shown that, no breakfast is not as good as a breakfast when you have children, because you want them to have, good energy while they're in school. But there was a study that looked at comparing no breakfast to breakfast with a lot of sugary cereals versus a euglycemic, a kind of a healthy breakfast that wasn't filled with sugar and so forth. And they found that the kids' performance was better with the healthy breakfast, and the sugary breakfast was similarly bad as no breakfast. And the blood glucose levels went up to about 120 with the healthy breakfast and went to like 140 with the unhealthy breakfast.
Yeah.
And so I use that as a kind of a poor man's, information to me that says to me, if my glucose goes up to 120, 125 after a meal, I feel that's successful. If it goes up to 150, I don't like it. And, it'd be ideal if it stays at 110, but I don't like panic or anything like that if it doesn't. You know what I mean?
I love your analogy of the dimmer switch. Actually, I think that's a really good analogy of, look, it turns on. The higher your blood glucose, the more and over time, the more that you trigger it, the more sensitive that your body will become to triggering that pathway. So, okay, so should we maybe move on a little bit to solutions? We've talked about some of these a little bit, but maybe both of you, can you kind of give an overview of what solutions are out there to help manage and minimize, where possible, activating this switch? Because I think it is really important, Rick, back to the research you mentioned earlier about longevity and the impact on health and all of these chronic diseases. So
I would tell people low carb diets, keto diets, like what Pete talks about, but low carb diets are going to be beneficial in general. Another one is to stay well hydrated. Don't eat a lot of salt either. If it's so salty that you're thirsty, that's actually associated with activating the polyol pathway. So stay well hydrated, eat healthy. I'm not telling you to never eat sugar. I'm not telling you to never eat a pancake, but what I'm telling you is that, try to cut back on those high glycemic carbs, the pancakes and the bread and the cereals, and cut back on that. Cut back on the potatoes and the rice. And the sugar and sweets, just cut it back. And if you can, go on a low carb diet or a keto diet, that will clearly be beneficial. And then GLP-1 agents, these drugs like Ozempic, they actually may have some kind of effects on this pathway. There's some evidence that it suppresses this pathway. And of course, they are very effective at causing weight loss, although they have their own issues. And Pete, maybe you want to say some additional things too?
Okay. So one of the reasons I work so hard in the biochemistry is that I would like to be able to respond to some of the questions that I've had over the last 6 years. And they fall into two main categories. The first is you've got a young person. I'm thinking of my daughter who just had my first grandchild. And her and her husband are pretty resilient. They are, they're pretty active and everything like that. And they're like, how should young people eat so that they don't get to be 60 years old and get the email that I got? And then you have the 60-year-olds. I think I work with a lot of people who are older, right? That's been the majority of the people that I work with. And they're asking, okay, if I can reverse my diabetes, get to the point where it's reversible, which is not always the case if they've actually got some severe damage in some of their organs. But if I reverse this, do I have to eat this way the rest of my life, or can I do some of the things that Rick just mentioned about, just cutting back on this or that? So I feel like you have two different issues. Are you chronically ill, metabolically ill, or are you a young person who's trying to navigate this standard American way of eating? And I think so far there are some lessons in this, which Rick already mentioned. But what I tell my daughter is that you should limit the amount of refined carbohydrate, the sugar and the fruit drinks and smoothies and all of that kind of stuff. Eat whole, real food. And this is perhaps, we haven't gotten to allulose yet, so I might as well open that can. And when you do go to make carbohydrate items, like my grandson just had his first year, and my daughter made a cake after interacting with Rick, and she made it with allulose, right? And then she also used some low carb flours and some things like that, so the kid could have a birthday cake. And I think that kind of stuff is very, very meaningful in the context of people that are healthy, right? When you move to the other realm where you're dealing with somebody who's older, like I am, who's metabolically sick, I have found that you've got to be significantly more aggressive with the initial lifestyle for sure. I don't think I would have reversed my prediabetes if I hadn't been really serious about being ketogenic, and I did that for 3 years. I have experimented since then with different things, carnivore, and also bringing some carbs back into my life because I'm an athlete and I work out really hard over the course of a week. And I've been experimenting a little bit with that, with whole food or whole carbohydrate. Anyway, and allulose may have a role there too, because I think when Neil and we both talked, Rick, you weren't there for that, but I talked about the fact what I know about allulose, and you can jump in because you know way more about this than I do. But one of the benefits is that it looks like it blocks the input of glucose and fructose at the level of the intestine. So I see a major benefit there when people are eating, mixed meals. One caution with the older set, serious type 2 diabetics, it seems like most of the clients I've had the last few years have also been super addicted to carbohydrate, refined carbohydrates. They all tend to have their go-to food. And with that, you do have to be careful about anything that's sweet, because it can drive them literally within a day to going right back to whatever their go-to food is, whether it's, ice cream or gummy bears or whatever it was, right? Mm-hmm. So there is that caution. You have to look pretty hard at the individual and determine, all right, can you do that safely or not? And there are other people that can. The world's a continuum. It's not just black or white, or one way or the other. So I think, understanding where you are and bringing kids up. I think this is really important, bringing kids up where they're not on that train of sweets all day long. So that once they become an adult, their idea of eating is a plate that is, significantly greater in proportionality of that kind of food in regard to the protein and the fat that is there.
Yeah. Thanks, Pete. So maybe, Rick, just to follow up, I would say on allulose, for those who aren't familiar with allulose, it would be great if you could just
Yeah.
summarize a lot of the clinical trials and research that have been done around the blood sugar control effects. I would say specifically, because I think that is really relevant as a potential tool to help manage blood sugar levels.
Yes. So we've talked about general aspects of diet and hydration and all those kinds of things, but there are some people who, really desire sweets, and most of the artificial and low calorie sugars out there, although they may not drive obesity, they tend to have negative metabolic or negative effects or neutral effects. And there aren't too many low calorie sugars. Actually, there's none except for one that actually seems to have metabolic health benefits. And so there is this sugar that looks like fructose. It's a natural sugar. It looks almost exactly like fructose, but it does not activate this biologic switch. And it's a rare sugar, but people have found ways to produce it. And it's generally regarded as safe, and it's in supermarkets, and there's a number of groups that are making these things, these chocolates and sweets with this sugar called allulose. And so it looks like fructose, but it seems to be neutral and actually metabolically health beneficial when people ingest it. And I was approached by a company called RX Sugar. They asked me to investigate the science behind it. And as I studied it, and we've even done some research on it, I've become convinced that it is overall a beneficial sugar. And it's sort of unbelievable because previously every sugar I found has been pretty bad. So I did join the company. I'm part-time with the company, so that's a disclosure. But what we found and what has been published in the literature is that allulose tends to lower blood sugar instead of raise it. And actually what is really effective is blocking that rise in blood sugar after a meal. And we talk about trying to target 120 or less. Allulose is very effective. If you eat it right after a meal, you can even eat it after a meal, like a 10-gram chocolate bar. It will block that rise in blood sugar. So and it looks particularly good for diabetics because it may reduce their insulin requirements. But the other thing is that it stimulates a hormone called glucagon-like peptide 1, or GLP-1. This is the same hormone that these drugs like semaglutide, Ozempic, all these drugs that are causing weight loss in people by dramatically stimulating it actually is, like giving a large amount of GLP-1. When you get semaglutide or Ozempic, you're basically getting a large amount of this GLP-1 activation, and it can cause weight loss. And allulose stimulates it from the gut. It turns on the production by the body of GLP-1, and that the GLP-1 can cause satiety and make you feel, not hungry. So another benefit of this allulose is that it sort of is a way to stimulate satiety and make you feel full, so you eat less. And so there's evidence that it can cause mild weight loss. So it's a pretty interesting sugar. It seems to have some other benefits too, like on the gut, and may even have effects on exercise. We're going to do a big study to see if it has a benefit on exercise. So it's an interesting sugar. And Neil, you are really an expert on allulose, and we also want to hear you talk a little bit about your big swim.
Yes, so maybe let me bookend on allulose, and then more than happy to talk a little bit about my, some might say, crazy swim coming up. And so for all the reasons you mentioned, Rick, and it was actually seeing yourself and Ben Bickman and Dom D'Agostino and all of these kind of legends of metabolic health last year, as I was digging deep into this and reading the research on stage at Metabolic Health Summit back in February, I think it was, that opened my eyes to allulose that I wasn't aware before, and all of these potential effects, positive metabolic effects. And so as I dug into the research, I got some of the product I tested myself, and I was just blown away by the personal results. And we'll link into the show notes, for example, the randomized control trial, the Jenkins study, which demonstrated that allulose can lower blood glucose on its own, but when it gets mixed with sugar or with carbohydrates, then it can actually dampen the glucose spike quite significantly. So as I realized all of this, one of the reasons why I decided to join RX Sugar was taking a step back and my own personal mission of how to help 1 billion plus people to become metabolically healthy. I just simply thought, well, if the pathway, the polyol pathway, the fructose pathway, as we discussed, on blood sugar control is one of the most important foundational things for metabolic health and all these chronic diseases. If the whole $120 billion sugar and sweetener industry was replaced with allulose, because it is just prevalent throughout the world, that I could think we could have a significant effect on the amount of chronic diseases which kill. Actually, 70% of deaths globally are related to these chronic diseases. Some 40 million people a year die from chronic diseases, and trillions of dollars get spent on the healthcare. And so I thought, well, if the world could replace that supply with allulose, then I think we could do a significant help to the whole world in helping to manage blood sugar levels. So that's the reason why I decided to join RX Sugar. And Steve, the founder and CEO, is a very mission-driven founder as well. So so I'm also happy to talk a little bit about my upcoming swim. So
yes,
what am I doing and why? So as part of raising awareness for for metabolic health, the challenge is called 0-2 Lomond. So it's going to be 0 calories, 2 brothers, myself and my brother, swimming Loch Lomond, which is a lake in Scotland, 22 miles long, 36 kilometers. We think it'll take us between 12 and 14 hours. And the reason we're doing this with 0 calories is really to try and dispel the myth, the current paradigm, that you have to fuel athletic endeavor with sugar and carbohydrates. And once your body knows how to burn and utilize fat as a fuel source, it will, happily do so. So it is a little bit on the extreme side, purposely so, really to act as a metabolic demonstration. And we're raising awareness for metabolic health, metabolic therapy, mental health, chronic disease, and really trying to drive some donations awareness to great organizations that are supporting this.
When is the event, and how can people, tie in and, make donations and so forth? When is the event?
So the event is in 3 weeks now. So it will be somewhere between the 18th and 20th of September. The lovely Scottish weather means we've got 2-3 days. We're going to figure out which day is hopefully the best weather-wise. And people can find out more. We'll link in the show notes at 0-2-lomond.com. So that is the website. You can find a little bit more. There's a little bit of education. And there are links to choose. There's 5 different charities that we're supporting. So people can then click on those and they can donate to the different charities, really to help raise awareness and raise funds for some great causes.
And is there a Loch Lomond a monster, kind of like the Loch Ness monster? Are you worried about your safety from these prehistoric dinosaur-like creatures that live in the bottom?
Well, I guess you never know, but we are doing it in Loch Lomond and not in Loch Ness. Although we did consider doing Loch Ness. I think Loch Lomond is it's just a beautiful part of the country, so not too concerned. But if they do come and say hello, hopefully they're nice and friendly. Maybe a little bit more concerned about the cold water. I live in Houston, Texas, so training for the cold water hasn't been super easy.
Give them a big allulose bar so that it'll stimulate satiety and they won't be so hungry.
That's a great idea. We can just drop them down exactly like flares in Top Gun.
Will you be wearing a wetsuit?
Yes, great question, Pete. So we will be wearing a wetsuit. Yes, given the temperatures will be pretty cold, and
Right.
safety is paramount. We will also have a safety boat with us at all times, tracking and supporting us. So yes, we're going to wear wetsuits. Very kindly, Sailfish have agreed to send us both a kind of a new top of the range wetsuit. So hopefully that keeps us a
Cool.
little bit warm.
Good luck, man. Good luck. I hope you guys just cream it.
Thank you very much. Yeah, no, we really hope so, and it ties in a lot of what we were speaking around today. So, the training for it, similar to you, Pete, I've experimented with pretty much, I would say, every diet there is over the last 10 years throughout my kind of metabolic health journey. So I've done everything from strict keto to carnivore, to vegan, to high carb, low carb, really to find, the impact on me. And where I generally settle is low carb Mediterranean style works the best for me. But for previous athletic endeavors, I have a little bit like you added in carbohydrates to fuel for the work required. But really for this one, I have been, I would say, pretty much strict low carb keto, just adding in enough carbohydrates to not stress the body out too much. Because I believe if you really restrict across anything, then it's back to the survival switch. If your body senses any threat, then it can start to work against you from a biology perspective. But really, a lot of those protocols I've been using and doing training too many days down at the swimming pool, just doing kind of laps endlessly. But looking forward to the yeah, a couple of weeks ago I did 30 kilometers, so it's like nine and a half hours. I got down at the pool at 6:30 in the morning, and I got back at like 5 p.m. But what was amazing about that, and I did the whole thing fasted, but I haven't been doing. A lot of people, I think, presume that all of the training is fasted. It's actually not. I've actually not done a huge amount of it totally fasted. And again, it's back to fasting is great, but too much fasting can put stress on the body, and then your biology can work against you. But this one I did, and I just felt okay. My shoulders and arms were pretty tired towards the end, as you would expect after 9 hours of swimming. But other than that, I just felt great because, especially, I feel when my brain and body is just running on ketones, it just got into this beautiful flow state of homeostasis because heart rate's not too high. It's like going at zone 2, for kind of 8-9 hours. And then once you get in that state, it's just like the body has this endless supply of very clean energy, body and brain. And it was actually, it was thoroughly enjoyable, although I do have to come up with ways to kind of entertain myself, given it's in a pool and you're just doing laps. But but it's been a really interesting journey doing the training, and I'm looking forward to challenge day.
Will
You'll
you
be the
guys
world's
be
greatest
live
lifeguard.
streaming or
Yeah, good question. So I don't think we're going to live stream, just because I think people, watching 12 hours of just two guys swimming in a lock, maybe some people, which is yeah, who knows? But we are going to we're going to at least record as much of it as we can and try and make a short documentary, really to kind of capture the before, the swim, and the after. And I don't know if reception on Loch Lomond will be enough to live stream, but we're going to try and set up a live tracker and then put it on the website, so at least you can kind of follow on and see our GPS traces, and hopefully they don't disappear as we get eaten by the Scottish monsters.
Yeah, good luck. I tell you, it's unbelievable what you're doing, and it's for such a good concept so good luck.
Yeah, no,
All
thank you.
right.
And it's really the only final thing on this I would say, and this is kind of captured on the website. We're not obviously recommending that anyone else do this. It's really to make people think that if you can fuel athletic and endeavor to that level without having to add carbohydrates, back to how we operate in everyday life, do you need to have that level of carbohydrates tying to back exactly what we spoke to today, and run the risk of too much triggering of the polyol pathway and the fructose, creation in the body. So it's all very much aligned to this, and maybe a slightly extreme way of making the point. But sometimes that's the only way you get interest and awareness, is by trying to do something that people just think isn't possible. So yeah, no, thank you for your support. Looking forward to it. I would say I know we've run maybe a little bit over the hour slot that we were aiming for. Any final, I would say, closing remarks, Pete, from your side, or Rick, from you?
I just want to piggyback on what Rick said about your event coming up. It's extraordinary. I definitely I want to hear about it and follow up. It's pretty cool. I know the cold water, and that's a long time to be in it. So, yeah, kudos to you. I think before we close, I think we all have one thing in common. I was thinking about this earlier today. We had 3 different people here. But what we all have in common is we do what we do because we want people to be able to improve their lives. And that's a pretty cool thing. And to tie it to an athletic event like this that you're going to have, that's going to be epic. The only thing I've done in my life, like you're about to do, is climbing big walls. And from the time you leave the ground until you get done, which is usually days, it's just dawn to dark, and sometimes after dark with a headlamp until it's over. And that's kind of what I think your swim is going to be like. That's a long deal. So good luck with that. And I'm looking forward to your success.
Yeah, I admire what you're doing, Neil. And I also admire what you're doing, Pete. I like the fact that you've come back to the science to try to understand things and, how we become good friends and collaborators from all this united areas of interest. So thank you all. Appreciate it. And
thank you, Rick. I mean, I piggyback on that. Our friendship is really important to me. And yeah, I think I found my niche. I really love trying to explain what's going on and focus on the science because,
Let's do a polyol pathway as an activation for the disease gout. Let's write that up together.
Yeah, okay. It's on my list.
All right, guys.
All right.
Perfect. Thanks very much. Really enjoyed the conversation today. Yeah, it's been a pleasure to spend this time with you guys and to get to know you. Certainly, Rick, over the last 6 months, and Pete even over the last few weeks. So I appreciate all of the amazing work that both of you have done in this space. It's groundbreaking, and I think looking back 20, 30 years time from now, I think this will be recognized as the central pathway. And so both of you are really trailblazing on that. So thanks for all of the amazing work that you have been doing and continue to do.
Thank you.
All right. Well, thank you very much for the conversation today. And I hope we get to do more of this. And you guys have a really good day.
Yes. Bye.
Likewise. Thanks, Pete. Thanks, Rick.
All right. Bye.